time for the technical session. This will be our first technical session of the day. In this session, we will have 3 papers dedicated to the load balancing and object mapping, which is one of the key features in Chan++. So our first talk will be given by Jonathan, who is a PhD student in Parallel Programming Lab. He will be talking about LU factorization on multicore supercomputers.
Okay. So this is a paper that was accepted at IPDPS. I'll be presenting this in China in a couple weeks at the conference. And so this is the implementation that won an HPCC Challenge Award and that Professor Cully was talking about. LU factorization is used to solve a system of equations. We focus on dense LU. Dense LU is used to benchmark, the top 500. Okay. Is used to benchmark the top 500 list. So it's a pretty common benchmark. And so the idea, just to quickly go over this, is that we take the n by m matrix and we put it and we block it. And these blocks need to be big enough for you get, or large enough for you get good performance in DGEM, which is the matrix-matrix multiply operation. But you want them to be small enough for you actually get good overlap in terms of communication and computation. Because as the computation progresses, each one of these block elements will be mapped to a processor. And so every processor will have multiple of these, and you want have communication and computation overlap. The computation proceeds along the diagonal, and I'm showing one step of the computation here. So for a given diagonal, we have 3 different regions. The first region is a set of A. These are the active panel blocks, as they're called. And along these active panel blocks, we actually go column by column. So this is very fine-grained communication and computation. For each column, we need to identify the maximum element. That will be the row that we need to swap with the diagonals row. And then we need to once that happens, data is broadcast to this entire column. And then we need to do a rank 1 vector-vector multiply that updates this entire submatrix. And so on this side, we basically have a ton of very fine-grained communication and computation. Now, once this is done, what happens is we have L blocks that are produced along this column. And those L blocks then get fed across the entire side of this matrix. So each one of these elements sends their L across. And these U triangular solves up here, which is on the order of what a DGEM is, it's just a different operation. They take that L data, and using it, they do the triangular solve, and then they produce the data that gets sent downward. And so a trailing update, the DGEM, a matrix-matrix multiply, can start when both inputs from the A and the U have arrived. And so this is done for every, along the diagonal, which is the path the computation takes. And essentially the things to note are that we have fine grains and we have coarse grains. So the DGEMs are very coarse. This is very fine grained. So we have, and then we also have basically 3 different levels in the critical path. So we have first the active blocks. The active panel blocks must compute. And then that releases work, the L that gets sent to the upper triangular. And then once those are done, all of a sudden we have a release of a lot of work. And this is the bulk of the computation, the matrix-matrix multiplies. So typically how this is done is with a block-cyclic mapping of the processor grid to, so you take the process grid and you stamp it across the matrix, and this is called the block-cyclic mapping. So for 24 cores, just to give a couple examples, I have 2 different configurations. On this side, I have a wide tile that's in column major format, as you can see. And on this side, I have a tall tile, which is in row major format. And so you can vary the aspect ratio, and this will have different impacts on performance. And you can also change whether it's column or row major, and that will also have other impacts on performance. So you take this process grid and you stamp it across the matrix. So if we have a matrix like this, we'll take that grid and we'll just place it basically on top of the matrix. And wherever that process grid tells us to put the block, that's where it goes. So in Chan++, this is very easy to do. We can define our mapping, and when we create the array, we have some options we pass in. We just set a map, and the mapping function is just a function that takes an xy coordinate for the block and returns the processor this going to execute on. And then we can just create that array with the block size and the matrix size. And I think the ops have already been set for this, so that would be passed in otherwise. And then char++ creates this char array, which includes all the blocks, and it manages their location. And so the optimizations I'm going to present are very easy to implement in char++ because it's just a matter of changing the mapping, and all these optimizations just happen. What I've done here is I have two different configurations, the two tiles I showed before, and I've mapped that to two different tiles, two different configurations here. On this side, I have the column major wide tile. On this side, I have the row major tall tile. And so there are a couple observations I want to make. Well, first of all, let me point out that I've colorized this by node. So I'm going to assume a 4-core node. Obviously, in modern architectures, we have many more cores than that. But just for simplicity, I'll use 4 cores, just so it's easy to show. And so first thing to note is when I have a wide tile, my parallelism along the row and column are different on both sides. So on a wide tile, I have a lot of parallelism along the row. Note I have 6 distinct cores along the row. On this side, I only have 4 because I have a tall tile, and vice versa along the column. So over here, I have 4 distinct processors. On this side, I have 6 distinct along the column. So by changing the aspect ratio, I essentially fix the degree of parallelism that's exploited along the row or column. And the other thing to note is that if we look along the columns here where the active panel will execute, depending on whether I choose row major or column major, I actually fix the number of nodes that will execute that active panel. So on the left-hand side, I'll have a lot of locality. In fact, the active panel in this case will all be executed on one node, which will be great for the reductions, the fine-grained reductions that happen. But on this side, when I use a column major, I'll have more parallelism along here, but it'll be across all these different nodes. And I could also, arrange this with a tall tile so it was in the other ordering. But either way, basically you trade off between, so this is a binary trade-off between having basically a few nodes executing the active panel or many nodes executing the active panel. So we attempt to address this with a knob we can turn that will allow us to adjust this. First, what we did to get an idea of so another thing I should say is the rank 1 updates that execute are basically memory bound. They have basically no reuse as they stream through memory. So what we did is on several different architectures, we changed the number of cores per socket that perform updates. This is in a micro benchmark. So so we're using a block size that achieves good degen performance, and it's all random data. So it's basically just streaming through memory. And as we increase the number of cores per socket, we calculate the efficiency going from 1 to the maximum number of cores on that given platform. So note that all of them drop substantially except for BGP, which is still drops, but it's okay because it's provisioned a lot better in terms of memory.
What are these numbers?
Oh, this is milliseconds. Sorry, and these are update times in milliseconds that it takes. So in this case, we just have 1 core performing updates. On this extreme, we have all 6 cores performing updates at the same time. And because of cache effects,
I see. So it's not being parallelized. It's when you say all 6 of them are doing, so they're doing 6 times more.
Right. Yeah. 6 times more work. Yes. Yeah. So if we actually, when we investigate this deeper, we graphed the number of L3 misses. So this is on the Istanbul architecture. We have 2 L3 caches, 1 per socket. So first what we do is so they're divided evenly. The number of cores we're using are divided evenly between the 2 sockets and the 2 L3 caches. So here we have the measured miss, or the expected compulsory misses, which are the modeled misses. So every cache line size is going to incur a miss. So that's what this line is. Now when we actually run the micro benchmark, we find that the actual number of misses increases superlinearly. Now the 1 to 2 is exactly what we expect, because it's these have their own L3 cache. So obviously there's going to be no disadvantage to using both cores. The problem is, though, if we pick a row versus column major ordering, we're basically stuck picking between this point or this point, which is really bad. When obviously, maybe there's a trade-off where these will be better, but it's obvious that 2 will be better in terms of locality, so we should at least pick that. But given the current orderings in block-cyclic, we can't do that. To fix this problem, we invented the notion of striding. And the idea is, so I have over here a row major order, and the idea is, so for the 4-core case, there are basically 3 different possibilities. You could have a row major, a column major, which I'm not showing, or you can have an intermediary. This is a stride equals 2. This is our new mapping, where we specifically adjust the number of cores per node that will be on the active panel. And so here, we stride, instead of striding by 4, we stride by 2, placing 2 cores per node along the active panel. Oh, no.
This is not a straight up, you can't
Yeah. Yeah, this is not a straight up block cyclic. No, they don't.
Really?
They, okay, yeah.
was intrigued when they showed this.
Yes. Yeah. Yeah. So this is, not row major or column major. This is an intermediary knob you can turn in between that will adjust this. To quickly, I don't want to get into the math a lot, but to quickly show how easy this is to do, this is the traditional block cyclic with the row and column major ordering. This is basically the function. I'll show it later on that we write in Charm. We just modify that function to add our parameter s, which is the stride. And it's not too complicated. There's no iterative anything you have to do. You just plug in the arithmetic and you get the stride. So to show the performance on the entire, for the entire run, on this side we have row major. On this side we have column major. So before, the best we could achieve was on this point, or column major, which was terrible. But now that we are able to move to 2, which happens to be the best on this architecture, it's really architecture dependent where this ends up, we're able to get higher performance with this optimization. The other, so that's the locality optimization. The other optimization I want to talk about is, before, if you remember, I was talking about the amount of parallelism in a row or column. So note that once we fix the aspect ratio, we essentially fix the amount of parallelism in the row or column. So over here, with a wide aspect ratio, we have 4 cores that operate in parallel, and 4 and 6 on this side, vice versa on this side. Once we fix the aspect ratio, it's fixed. So what we want to do is there may be an advantage or disadvantage to picking one aspect ratio. In fact, if we look at this, this may execute the active panel faster because we have more cores along each column. So we may want to pick this, but then we have the disadvantage of our triangular solves, which are on the critical path, will go slower, or may go slower because the degree of parallelism we're exploiting is less. So the idea is, well, first what we did to get an idea of whether this is beneficial or not, is we benchmarked the amount of time each active panel steps. So this is going column by column in the active panel as we factorize it. And we measure how long each active panel step takes with differing grid sizes. So the wide grid only has 8 cores along the column. Square has double, and tall doubles it again. And so we get a speed up as we increase the number of cores along the active panel, which is expected. And it's not as, so the first jump from 6 to 3 is basically a perfect speed up. From 3 to 2, we're getting probably bound by memory. But we still get a speed up. And since the active panel is actually on the critical path, even if you don't get perfect efficiency, you still want to do it faster if you can. So now I'm going to show you the entire run, though. So this is the aspect ratio. Tall on this side, wide on that side. Now note that the best points are actually in the middle. And the reason for this is because even though the tall makes the active panel go faster, which I just showed, it actually slows down the triangular solves, which are also on the critical path. And the wide has the problem that the critical path is extremely slowed down. So the idea is to take the tall process grid and fix it so there's more parallelism along the row. So here's our traditional block cyclic on the left, and here's our block cyclic with rotation. And so rotation, the idea is you take the tile and you rotate it by a certain amount. And what that does is that will put more processors along every row in this case. So here we rotate it by 2. So notice, basically all these are just rotated by that amount. And now instead of only having 4 cores along each row, we now have, well, if we were to extenuate this out, we would have 12. In this case, I'm only showing 9. So again, this is a simple formulaic process of adding a R value that will rotate the block. Now for performance, on this side I have no rotation. So this is the cores performing triangular solves. So on this side with no rotation, we have very few performing triangular solves. And on this side, I have an R equals 1, which is basically the maximum rotation. So you rotate it by 1 each time, which will give you essentially the maximum period the rotation will have, which is all the cores perform triangular solves. Now there's a trade-off, because at some point you don't want too much parallelism because you're bounded by network and other things like that. So it is architecture specific. But there exists some point, and it's not, the first point, where once you apply an adequate amount of rotation, you get the highest performance. Now, from a theoretical standpoint, it would seem that maybe a square tile is actually the best because of the ratio, iso-efficiency standpoint, of the ratio of, the number of cores, on both sides. And so what we did to test this hypothesis is we actually graphed this, divide it proportional to the square root of the number of cores. And when we do this, we find out that a rotation that causes the number of cores along the row to be equal to what it was back when it was a square tile is actually the right amount of rotation to apply. So essentially, we take a tall tile, which gives us the advantage of the critical path moving fast for the active panel, but has the disadvantage of the reduced number of cores along each row, and then we rotate it to restore it back to what it had in the square. And we show that once it's rotated that amount, that's a sufficient amount to get the best performance. Of course, these optimizations can be applied together, and those are the results we present in the HPCC challenge, etc. And so the interleaving is a little bit different than what I showed before. When you stack them on top of each other, but you basically get the same thing here, that you have some number of localized cores in the same node, and then some amount of parallelism you can adjust. And we can also add both to our formula, and that all works out. Now we have an S and an R parameter we can turn. And this is the code, the mapping code for the right-hand function. Just to show you real quickly, in Charm++, the mapping code is completely independent of the application. So you just write a mapping function that takes your x and y coordinates, and then you just basically apply the function and return the PE number that comes out in the end, and you have this new mapping. So data movement overhead. Let's say we have a traditional block-cyclic and we're trying to move it into a rotated or strided configuration. So for 528 cores and 2K cores on Cray XT5, and for matrices sizes that we use that were highly performant, we measured the data movement percentage of total time to move it into that configuration. We found it's about 2% on 500 cores, about 1% on 2K. Our performance compared to the best square grid that we achieved, so before the best we could achieve was using the square grid, we found that striding yielded an 8% increase, rotation yielded a 3% increase in performance, and combining these yielded about 11%, and this corresponded to a 7% increase in peak performance on the Cray XT5. And so this is how we're able to achieve about 67% of peak, going from 120 cores to 8K cores on XT5. And this is to quickly show, this is our scaling. So this is the Cray XT weak scaling line. This is 75% of memory occupied, and then this is strong scaling on BGP. Any questions?
So, have you considered looking at some slightly different LU factorizations? I know this is, of course, this is the factorization that you have to use for this benchmark, right? So, right. But there has been work on different activity schemes that are still stable, but that let you speed up the critical path along the panel factorization.
Right. Yeah, we're actually investigating using like recursive factorization schemes or communication avoidance, stuff like that. So that's in the works.
Would that change the tuning parameters, like the different constants in that block-cyclic layout?
Yes, I think it will, but it's hard to tell how much of optimization still apply in those different regimes, and we're still testing that and investigating theoretically whether they still apply.